Good morning. Welcome to a tired Thursday. We said. Oh, that's anyway. Yes, here we are on a tired Thursday, doing some math together. So thank you for showing up for your learning. I am going to go over the various question types that will be on our Unit 3 test tomorrow, and show you the roads to a solution for all. So here we have situations about exponential growth. A government is creating a breeding program for their giraffes, and they create this program in 2021. And the number of giraffes grows by 23% each year. I would call this a very successful giraffe breeding program. If there's currently 2,400 giraffes, let's create an equation to model this situation. So we have to think about the initial value, and those we might call that V, and then the growth factor, which is always 1 plus the rate as a decimal. So let's take a look at those things and what they are for this situation. So our V is 2,400, all right? Our growth factor, we usually call growth factors B, okay? B is the growth factor, V is the initial value, and they're going to create equations that look like amount is a function of time such that V is equal to V multiplied by the growth factor B raised to the power T. So in this case, we have our V is 2,400. Our B is equal to 1 plus 0.23. 0.23, that's 23% as a decimal. Careful when you do that, get the decimal in the right place. And so we have the amount of giraffes is a function of time. Time is a number of years. And it's going to start at 2,400. Going to be multiplied by 1.23. Oh, that's funny, 1.23. Raised to the power T, where T is the number of years since the breeding program started. And we have year 0 equals 2021. So if you want to know how many giraffes are going to be in existence in 2040, 2040 would be 20 years from now, then you would do 2,400 multiplied by 1.23 20 times. So you'd raise that to the power 20. And that's how you set up exponential growth equations. Sorry? 2040. Did I say 2040? I thought I said 2041. The brain fog is strong today. Maybe it is a tired Thursday. Okay, let's keep going. Now we have exponential decay. So here, when we're setting up exponential decay situations, we have now a group of aliens who begin an aggressive abduction program, removing 12% of a city's inhabitants per month. If the population is currently 55,000, we want to know when will that population be 8,000? So in order to do that, we'd like to have an equation. So we would say that the population here is a function of time, and we're going to have the initial value, 55,000, multiplied by the growth factor B raised to the power T. T is months, because this is per month. So you're just aware of that. You're going to input a number of months here and then put the number of months there, and that's going to lower the population by 12%. How do we create this B value? B here is going to be 1 minus 0.12. Okay? The reason is this is the percent decrease. You could say it's growing by negative 12%, or you could say it's decreasing by 12%. That would be a synonym. So we're going to take 100% of the population, and we're going to remove 12% of it every month. So that's going to give us 0.88, and we're going to raise that to the power T. Okay. So if we want to know how long will it take for the population to reach 8,000, well, there we know that for some P of T, for some value T, we're going to have this equation equal 8,000. So then we're going to set this up here like this. 8,000 is equal to 55,000 multiplied by 0.88 raised to the some power t. And then we divide both sides by 55,000. We're going to get 8 over 55, which is some power of the golden ratio, the inverse of the golden ratio. It's also math I don't want to do in my head. It's 0.14545454. 0.1454. So we'll go 0.15, 15%. How long will it take for the population to be 15% of what it is right now? Some of you are asking, how do we do this for half-life? Like, how do I tell when there's 15% of the material left? And you would have an equation that looks something like this. You'd put the 15% over here as a decimal. You'd have 0.88 over here. And it's going to be raised to some power t. And now, at this level, we're still limited to guess and check or graphing to solve these. So I would create a table that looks like this. So I'm going to test different values of t, and I'm going to be raising that to a certain power. So what looks like a good one to test first? 5 months? Maybe a few more months? Maybe 8 months? Let's test 8 months first. So I'm going to do on my calculator here 0.88 raised to the power 8 equals 36%. So that would be 0.36. That is not enough months. The aliens need more time to reduce the population. So I am now going to clear. I'm going to go 0.88 raised to the power, let's go 16. Let's double it. Equals, 13%. So when I did 16, I got very close. That's 0.13. I'm getting pretty close here. Now I'm going to guess a number lower. I'm going to guess 14. 0.88 raised to the power 14 equals 17%. I went too high. I was too aggressive. It looks like 15 is going to be our best answer. 14, so that's 0.17. And then if I go multiplied by another 0.88 equals, yeah, that's 15% right there. So 15 is the number. 15 gets me 0.15. This is rounding to the nearest percent, the nearest percentage of the population. So therefore, I would say, therefore, the aliens require 15 months or a year and a quarter to reduce the population. To 8,000. Okay. Now, people seen the original Avatar? In the original Avatar, they're out for unobtainium, some ridiculous science fiction material that everyone wants. Okay? So I've said that a 144-gram sample of unobtainium 89 has a half-life of 5 seconds. So now we need to really take a look at this idea of half-life. So when we're setting up half-life equations, we're going to say that the amount is, again, a function of time. It's going to be behaving exponentially. You're going to have the initial value there multiplied by 0.5, and you could write 1 over 2 here, no problem. Raised to the power t divided by the half-life, which is given you. A challenging question would be, find the half-life of this material if there's such and such left after such and such time. That would be tricky to solve for this bottom h. Not so tricky. Anyway, here we go. If it has a half-life of 5 seconds, then here we would put that half-life of 5 down there, and t would be some number of seconds. Okay. So here is our equation for this situation. We would have the amount of unobtainium is a function of time, t seconds. So it's a time domain function with t measured in seconds. It's equal to 144 multiplied by 0.5 raised to the power t divided by 5 seconds. Okay, So this should make sense because when time is 5, when time is exactly 1 half-life, you would have 5 divided by 5. You would be raising half to the power 1. And then you would say, okay, that's going to be half of 144. That will output 72. So you're satisfied. You know your equation is working at time 1. Try time 10 seconds. 10 divided by 5 is 2. This raised to the power 2 is 0.25. You would have a quarter of this left, 36. So if we want to know how much of this science fiction material will be present after 21 seconds, we just evaluate our function. A at 21 seconds would be equal to, this might also be your interest level in the movie after 21 seconds of it, is equal to 144 times 0.5 raised to the power 21 over 5. 21 over 5 is not a cute, not a nice number, but it's easily punchable on my calculator. So now I'm going to punch it, observing Bedmas. Quick Bedmas lesson, do this exponent first, and do this division first as well. 21 divided by 5, so I do 21 divided by 5 equals, okay, 4.2. All right, cool. So I'm going to raise 0.5 to the 4.2 equals, okay, I get about 5%. And then I multiply that by 144, and then I get my answer. 7.8 grams of this stuff is left. So 8 grams is left at 21 seconds. So that's equal to 7.8. 7.8 Gs. So therefore, there will be 7.8 grams of this material left at 21 seconds. But what if I want to know how long will it take for there only to be 10% left, eh? Oh, okay, well then, now I know that I don't care about the initial amount. I don't care about the final amount. I just want the final amount divided by the initial amount to be 10%. So that's going to look like this. 10% is equal to 0.5 raised to the power t over 5. Okay? So now I can write that as a decimal. 0.1 is equal to 0.5 to t to the something. Now create your table. T, and then you're going to test some values. We got pretty close to 10%. We want about 14.4 grams, and we got just a little bit under half of that. So actually, we have the answer here. It should be about 16, but it's going to be a little bit more than 16, a little bit less than 16. So anyway, I'm going to start my guessing, just based on the result of this one, around t is 15, let's say. So let's go t is 15, and that's going to give us 3 half-lives there. So I'm going to raise 0.5 to the 3 is equal to 0.125. So this gives me 0.125. So that's not quite enough. Let's try 16. That's going to be a little smaller. 16 divided by 21 equals 0.76. Okay. So, 16 divided by 5. 16 divided by 5 equals 3.2. So now I'm going to raise 0.5 to the 3.2 equals 10.1. Sorry, 10.8. So that's 11. 0.11 or thereabouts. So let's try 17. 17 seconds. 17 divided by 5 equals 3.4. 0.5 raised to the 3.4 equals 9.5. 0.095. Okay, so there's my answer, 16.5. I'm satisfied. I've gotten close enough. I could get a lot closer with decimals, and I could get an exact answer with logarithms next year. So it's going to take a little while. Okay, so therefore it will take 16.5 seconds for there to be 10% left. Now let's review our exponent laws. We have product of a power law. X to the a multiplied by x to the b equals x to the a plus b. Okay. We have x to the a divided by x to the b is equal to x to the a minus b. We have x to the a to the b how have you not all made a rap about this? Is equal to x to the AB. And we have x to the 0 equals 1, which is just a variation of this law. And x to the negative 1, x to the negative a is equal to 1 over x to the a. Again, I can create that with this law. And then another law that I have here for exponent laws is rational exponents. And I'm going to just come down here to rational exponents. X to the a over b is equal to the b root of x raised to the power a. You could also write it as the b root of x all raised to the power a. Or if you're not a maniac and you like doing things like I do, you'll say x to the 1 over b raised to the power a. I find this to be the most useful way to write it down. This is just a variation of your product of a power of a power law. It's exploiting that to open things up. So we have some various questions that are in here. Should I do one? Yes, because we have several in the test. So here's an example of one of these question types. 7D. U raised to the power negative 2, v to the 3, and let's make it more complex. Let's raise that all to the power 2, divided by u to the minus 3, v to the minus 2, and let's raise that to the power negative 3. So first thing that I'm going to do, I have to do these outer exponents first, because Bedmas, exponents first, and then you can go inside and do this, all this stuff here. So do this exponent first. So I'm going to raise these all to the power 2. So then I'm multiplying the powers. So this is u to the negative 4, v to the 6, divided by, I can multiply powers here too. Okay, so that would give me u to the 9, v to the 6. Then this is equal to u to the negative 4 minus 9, because I'm dividing powers here, and then v to the 0. So this is equal to 1 over u to the 9. It's equal to u to the negative 9. It's equal to 1 over u to the 9.
1 over 13. 1 over u to the 13.
Thank you. Yeah, 4. Why did I write down 4 minus 5 here? Oh, it does. Why did I think that was a 5? That's strange. Yeah, thank you. This is minus 4 minus 9 is minus 13. Thank you. Cool. All right. So now with rational exponents, yeah, you'll get questions that ask you to do things like write as a rational or write as an exponent. So I'll give you an example of each. If I have 125 to the 4 over 3, well, that's equal to 625. But here, if I want to do this step by step, I could write this as the third root of 125 raised to the power 4. And that's equal to 5 raised to the power 4. And that's equal to 625. Okay? Or I will give you questions like write as a rational exponent. Well, this is x to the 4 over 3. Okay? Well, why is that? This number here goes on the bottom of the exponential, the rational exponent. This number here goes on the top. You could rewrite this as x to the 1/3 just rewriting that rational exponent as a fraction. Sorry, this radical as a fraction, and then raise that to the power 4 and use your power of a power rule. This is x to the 1 over 3 multiplied by 4. And then that will give you 4/3. Same thing. We'll also have exponential expressions on the test. So this is something that doesn't show up in your review. So let's see, how can we solve these types of questions? Well, we have unknowns that are in the exponent. If we could only create a common base, we could equate the exponents, and that will help us solve these types of problems. So here, I see that 64 and 512, they're all powers of 2, but they're also powers of 4. So, but they also powers of 8. Okay, so let's use the biggest possible base. It's going to make this simpler. 64 is 8 to the 2. So let's write that as 8 raised to the power 2 raised to the power x plus 7 equals 500. Oh, sorry. I mentioned the brain fog is strong on a tired Thursday, right? This is 8 to the 3. 8 to the 3 raised to the power x over 2. Okay, so now I do my power of a power law, and I get 2 times x. So this is 2x plus 14. And this is 3x over 2. So 2x plus 14 equals 3x over 2. Okay, when I multiply this, I get this. When I multiply that, I get that. The bases are the same, so the exponents are the same. Now, move all your x's to one side and all your numbers to the other. So let's subtract 2x from both sides. We get 14 is equal to 3 halves minus 2. So that's 3 halves minus 2 halves. So that's negative 1 over 2 times x. Multiply both things by negative 2, and you get negative 28 is equal to x. There, done, final answer. And then that's something that's pretty awkward to check on a calculator up here. These are going to be big numbers. Big numbers. Okay, so now over here, let's take a look at this one. 9 to the negative x plus 3 is equal to 1 over 27 to the x. Okay, these can all be written as powers of 3. So 9 is 3 squared. So I will have 3 to the 2 raised to the power negative x plus 3 equals 3 to the negative 3. That would be 1 over 27. 3 to the negative 3 raised to the power x. Okay, so now we have 2 multiplied by this. So this is, and I'm removing the base at this point because I have an exponent that I can solve for. This is 2 times negative x, which is negative 2x, plus 2 times 3, which is plus 6, is equal to negative 3 times x, negative 3x. Okay, let's add 2x to both sides, and we get 6 is equal to negative x. That's adding plus 2x on both sides. And then that will give us our answer. Multiply both sides by negative 1, and we get negative 6 equals x. Cool. I think it's cool. Yes. Yes, that makes sense. Now let's graph some functions. Here is a function, f of x equals 2 multiplied by 4 over 3x. When I printed this came down here. That's kind of awkward. Okay, so let's test some values. We're going to fill in this guy here. So let's try looking at, I think negative 4 is a good place to start. Let's look at negative 4, negative 1, 0, 1, and 4. Let's try these 5 values, and then we'll get a way to put a curve through all this stuff. So I just plug in things on my table of values and solve. The 0 should be pretty easy because that's when this exponent is 0, so the output will be 2. So that one I can do in my head. Okay. If I have 1 here, this would be 4 over 3 to the power 1, so I just multiply 2 times 4 over 3 would be 8 over 3. 8 over 3 is a little bit less than 3. So I can plot those 2 points right away. So this is going to be here, my my y-intercept. And then at 1, it's a little bit less than 3. So that's going to be there. And then here at 4, I'm going to raise this to the power 4. So it's going to be 4 over 4 over 3 to the 4. So that's calculator time there. 4 divided by 3 equals, raised to the power 4 equals, oh, that's 3.16. Of course, it's 3.16. Yeah, so 3.16 then times 2 equals 6.3. So this is 6.3. If you said, well, here, Mr. Jennings, you could just throw that to the bottom of a fraction, I'd say, can you? No, not quite. So let's see that. So here, 6.3. So I can put that on too. So that's at 4, 6.3. It's a little bit bigger there. All right. The asymptote here is still going to be the x-axis. But let's test -1. 4 over 3 to the -1 is 3 over 4. 3 over 4 to the 2, that's 3 over 2. So that I can do in my head. 3 over 2. That's 1.5. So that goes down to 1.5 there. I can do 2 as well by multiplying by another 3 over 4. Anyway, let's do our -4. So this would be 4 over 3. 4 divided by 3 equals 1.333. Raise that to the power -4 equals 0.3 multiplied by 2 equals 0.632. So I can put that one down there as well. 0.6 is a little bit bigger than a half. This is about there. And now it's time to see if I can draw a curve through these points. He's learning, folks. He's learning. So there's our curve. And that's a pretty good graph of it. And then I would be satisfied using this graph, accepting this little lumpy bit here, to find solutions to this type of problem. F of x equals 1/2 to the x plus 2. So now, instead of having a number here that was slightly bigger than 1, a number slightly bigger than 1 created exponential growth. Here we're going to have a number 1 over 2 to the x. That should create exponential decay. In fact, this could be a half-life type of equation. But it has a c value of plus 2. So the first thing that I know is that I have a horizontal asymptote equals, so it's, I shouldn't have an equals, there's y equals 2 is our horizontal asymptote. So let's graph that here first. Here's our horizontal asymptote here. So we shouldn't cross that line, even though that's not really the line. Okay, so now let's fill in our table of values. We have 1/2 x plus 2. This is going to be a little bit more dramatic in its function, so I'm going to use values tighter to this tighter to the y-axis. So I'm going to start at -3, -1, 0, 1, and 3. Let's try these values. We get to choose. Doesn't matter what values we choose. You choose any values you want. Okay, so let's put that in. 1 over 2 to the -3, that's 3 to the 2, so that would be 10. I can do these in my head. -1, you can use a calculator if you need. That's going to be 4. 0, this is going to be a 1, so that's going to give us 3. Yep. Yes, sure thing. Raised to the power 1, so that'll be 1/2 plus 2. This is 2.5. And 3, this is 1 over 2 to the power 3, so that'll be 1 over 8 plus 2. So that's 2.125. So now let's plot our points. -3 was to the 10, so that was all the way up here. Thereabouts, I think, is about the 10. -2 would have been, this is 4, so that would be 6. This is 1, 2, 3, 4, 5, 6. This is 2. Didn't have it on my table of values, but I can do that in my head. There, there, there. And then we did 3 was there. So this one is coming down. Not bad, eh? Not horrible. So there's our exponential curve. Again, I get some lumpiness in there, but that's just because I'm like shaking with delight at graphing these exponentials. So now here, f of x is equal to 1 half 0.5x plus 2. Now we have a k transformation, a d transformation, a c transformation. My goodness, isn't this delightful? So let's take a look at what we've got here. 1 half to the 0.5 minus blah, 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 blah. Okay, so let's say that we had brackets here, be a little nicer, wouldn't it? So let's do this one. Okay. So now I know that this will create a 0 here when x is -2. So I'd like to look at -2. Let's look at one value before -2. We'll look at -4. And then we'll look at 0. Then we'll look at 2. And then we'll look at 4. Okay? -2. If I put -2 in here, -2 plus 2 is 0. 0.5 times 0 is 0. So this is 1 minus 1. This gives me a 0 here. So I have this point, -2, 0, as one of my points. -4. -4 plus 2 is -2. -2 times a half, -1. So 1 half to the -1 is 2. 2 minus 1 is 1. I could also graph my horizontal asymptote here. My horizontal asymptote is the horizontal asymptote is y is equal to -1 because that. Okay? That's where I get my horizontal asymptote. So let's graph it. Don't cross that line. And so this looks to be coming down this way, going through there, and then down and along that way. Okay, so it's 0. 0 plus 2 is 2. 2 times 1.5, 2 times a half is 1. 1 half minus 1 is 1 half. -1 half. So it's there. Yeah.
I have a question about the brackets in the expression. Or in the function, sorry.
Yeah.
Did you just forget the brackets?
I forgot to write the brackets there. Yeah. It's nicer with brackets. So I'm doing it with brackets. Change that. So when 2 plus 2 is 4, so 4 times that is a half. So that's that makes this to the 2. And so that'd be a quarter minus 1 would be -0.75, -3/4, -0.75 there. And then if I have this as the 4, 4 plus 2 is 6. 6 times 1 half is 3. This to the power 3 is 1/8. So this would be -1 plus an eighth. So that would be -0.875. Thank you, Siraj, for confirming my mental math. So that would be, give us the 2 here is down here. And then the 4 here is down here. And it looks like there might be something interesting happening at -6. So let's do -6 as well. We'll do it up here, -6, so that we can see the function. -6 plus 2 is -4. -4 times a half is -2. 1 half to the -2, flip it, is 2 to the 2. 2 to the 2 is 4. 4 minus 1 is 3. So that gives us this point here, 3. Hold on one moment. All right. So we've got a pretty good sketch here so far. So let's go through and we'll sketch our doodad here. This is coming down. It's going to go through these points. Something like that. That's this exponential function. So these are concepts that we need for tomorrow's test. So let's open the floor to questions. Are there other question types that we haven't looked at today? Now, I didn't do this as a transformation of some original function. I just plugged and chugged. And I like plugging and chugging with these. If I want to, I can say that my parent function here, some kind of g of x, was equal to 1 over 2 raised to the x. And then we apply to k equals 0.5. We apply to d equals plus 2. And we apply to c of negative 1. Okay? Let's do that in another color. Let's take a look at what the original function looked like. 1 over 2 to the x, that goes through here. At 1, it's a half. Its horizontal asymptote comes down here. Super close already by 7. And then over here it would be 2, and then it would be 4, and then it would be 8 already, so it would be up here. This was the parent function. Whoops. What was happening there? That was just my excitement at being almost finished our test review. Okay, so this was the parent function. And then what did we do? We stretched it horizontally by factor half. Notice that our parent function is much slopier. We stretched it by factor half. And then this point didn't stretch. It stayed the same. But it moved 2 this way and down 1. So that's this point there. This point here got stretched by factor half, moved down 1 and over 2. It's that point there. This point here got stretched by factor 1/2, so it's now over here, went down 1 and over 2. Okay. This one got stretched by factor 1/2, so it went there, down 1 over 2. Okay. So let me just highlight some of these points. This one went over here first, that's K. And then it went down here, that's C. And then it went over here, that's D. Okay? This point here, that's K. It does not change from K. It went down here, that's D. It went over here, that's... That's not D, that's C, man. Get it right. Get it right. That was C going down and D going to the left. And then we could do that point, or we could do let's say this point here. This one, its K is a little more dramatic. It gets stretched by K going there. Notice it gets, oh sorry, no, it goes the other direction from K. I've mentioned how brain foggy I am, right? So let's take this point here. From this one, for K, it went over here. That's K. And then it went down 1 from C, and then went back 2 from D. Okay, and so that's this point here on the new function. So that would be transforming point by point from a parent function. Wouldn't be hard, but I find that just plugging in, plug and chugging with your function is just as easy to graph these. Just as easy. Okay. Useful to understand them though as a transformation, and they're beautiful functions when we start transforming them. If we only had so much more time. Okay, bye everyone. I hope your math practice is fruitful. I look forward to responding to some emails tonight if you have things that you want to go over. And the beginning of class tomorrow, we will have more time for questions. I'm also here early, so if people want to come early and ask me questions about exponential functions, I'm always delighted to see you when you come early and ask me questions. TTFN.